So here we are in section 3.2, starting it out, and we're going to talk about something called L'Hopital's rule. Here we have a hammer. You may or may not be able to tell this is a hammer, but I drew it because L'Hopital's rule is one of the most useful tools that we'll come across. So it is a very, very useful tool in calculus, and you'll especially see it a lot in calculus too. So this little rule gets used and is really handy. So here we have two mathematicians. Over here we have Guillaume de l'Hopital, and then on the right is Johann Bernoulli. So in 1694, Bernoulli actually discovered the rule that we're going to be talking about, but back in 1696, a couple of years later, it was L'Hopital who published a math book, and it had this rule in it, and the rule became L'Hopital's rule, even though Bernoulli actually discovered the rule. So the lesson for all of us is when you discover a super useful math fact, publish it yourself. Let's talk about the context of why where this rule comes from, and when it's helpful. So we're remembering that the idea of a limits are a really big idea that encompass a lot of different types of limits, and we've definitely seen some limits needed for the type of calculus we've learned so far, differential calculus. And that's just a small amount, very tiny amount within the larger framework of there's a lot of different kinds of limits. But so for example, the limit as h goes to 0 of f of x plus h minus f of x over h is a limit that we use all the time because this equals f prime of x. It is the derivative, and that's a really important limit. So important. We've used this over and over again. But it's not the only limit. There's a lot of different kinds and different limits that come up in mathematics. And so there is something called an indeterminate form. So when we're dealing with limits of what's called indeterminate forms, it's where we're trying to find a limit involving something that has a 0 over 0, or maybe an infinity over infinity. And these are indeterminate because we cannot determine things about 0 over 0. We cannot determine things about infinity over infinity. But L'Hopital's rule lets us change the question in a way that we are able to find these out. So within the large sea of limits, we occasionally will come across limits that look like of things that are 0 over 0 or infinity over infinity, and those are not just solvable as they are. We have to somehow change them, which L'Hopital's rule is going to help us with. But this is a limit. L'Hopital's rule involves derivatives. So this is actually a limit that gets helped by derivatives, whereas this is a derivative that gets helped by limits. So as we've been talking about for a couple months now, limits, this is a limit that helps us find the derivative. What we're going to see is in a totally different type of problem, it's actually going to be the derivative that helps us find some rather difficult limits, these indeterminate forms. We're going to remember that, a function f of x is just sitting out there, and then at a certain point we can write or draw a tangent line at a point called a, maybe x equals a. But as this point, as we zoom in closer and closer, the function and its tangent line approximation actually become indistinguishable if we're able to zoom in closer and closer and closer. So as we zoom in closer and closer, a function and its tangent line become indistinguishable. We zoom in really close to x equals a, and we can hardly tell them apart as we get closer and closer. And so also remember or recall that if, for example, the 0.37 is on f of x, and we also know that f prime at 3 is 4, so in this function, 1, 2, 3, 7 is sitting on this function. And we know that at x equals 3, the derivative is 4. That's the slope of the tangent line. We have enough information to write the equation of this tangent line. So we know that this tangent line is y minus 7 equals 4 times x minus 3. So that's just jogging our memory, and in general, we know that a tangent line approximation would be y equals f prime at a times x minus a plus f of a. This is just taking that negative 7 over to the other side. So the derivative at that point a times x minus a plus the function evaluated at a. Okay, so this is a fact that we're going to use and that Bernoulli used to come up with what's called L'Hopital's rule. That we are asked to evaluate a limit as x goes to a of f of x over g of x, but we're also told that f of a equals 0 and g of a equals 0. So we can't just plug in a because we would get 0 over 0, which is, we can't determine anything from that. That doesn't give us information. The 0 in the denominator is just not helpful. So when we have 0 over 0, we're going to try something else. So we try to look at the limit as x goes to a, and now instead of saying the function, we're going to give the tangent line approximation. Remember over here, we learned that f of x, or y, can be approximated by this tangent line approximation if we're close to a, and that's what we're going to use. So instead of writing f of x, we're going to write the tangent line approximation, which is f prime at a times x minus a plus f of a. And then this is going to be a tangent line approximation for g near a. This expression is a close substitute for f of x when we're close to a, which we're trying to get to. And this expression here is a close substitute for g of x when we're close to a. So we wanted to find this, they asked us to find this, and it's not possible because we have 0 over 0. So we're going to substitute f of x for this, the tangent line approximation, and g of x for this because we're close to a. They're very, very close. But we already know that f of a equals 0. So that's 0. And we also know that g of a equals 0. So that's 0. And what we now have is the limit as x goes to a of f prime of a times x minus a over g prime of a times x minus a. And we can definitely do some canceling here. Same thing on top and bottom, same factor on top and bottom. And so we end up with this equaling the limit as x goes to a of f prime of a over g prime of a. This is a big deal. This is saying that in certain conditions, this condition right here, if you start with trying to find the limit of f of a over g f of x over g of x as x goes to a, but you've got zeros on top and bottom, you actually can just find this limit, and that limit is sometimes much better. So let's look at an example. So say that we were asked to find the limit as x goes to 0 of natural log of 1 plus x over x. If we just try to plug in x equals 0, we will get 0 over 0, and that's because so if we just try to plug in x equals 0, we get natural log of 1 plus 0, that's natural log of 1, and that is 0. And then, of course, the denominator is 0. So we get a 0 over 0, and we're in the case that we were talking about earlier. So we're going to use L'Hopital's rule. Which says that if you have this limit but you're getting 0 over 0, why don't you take the derivative of the top and the derivative of the bottom, and that limit is actually going to be the same thing. So that's what we're going to do. We'll take the derivative of the top, and that will be, so this limit here, because of L'Hopital, will equal the limit as x goes to 0 of the derivative of natural log of 1 plus x is 1 over 1 plus x. And the derivative of x is just 1. So this was a derivative. It was just the derivative of natural log of 1 plus x. This was a derivative. It was the derivative of x. And L'Hopital's rule says that we can do this. And this is awesome because then this becomes the limit as x goes to 0 of 1 over 1 plus x over 1, which is just this. And if we now try to plug 0 in for x, we just get 1 over 1. That's totally legal. This all equals 1. So we've just found out that this limit that we were looking for, but it kept giving us 0 over 0, so we couldn't determine anything. The answer, because of L'Hopital's rule, is 1. The limit is 1.